So I hope you watched the introduction video, and now we can try example 1. So it says find the orthogonal trajectories of the family of curves y equals e to the power c1x. So in other words, what we need to do, we need to find another family of curves such that all curves in this family are orthogonal to all curves in that family. Well, and if they're orthogonal, then that means that their tangent lines are negative reciprocals, right? And that's how we're going to connect this family with its orthogonal trajectories. Well, let's start by describing slopes of the tangent lines for all those curves, and as we already talked about that, derivative will represent the slopes of the tangent lines. So let's start by finding the derivative. So let's say it's step 1. So I'm gonna write it in general, even though we already said we're gonna find derivative right now. Let's say it this way. We're gonna find the differential equation that describes this family. So you'll see how it works, but I'm gonna write down find the differential equation that describes this family of curves, which is y equals e to the power c1x. Well, we do start by finding the derivative. So what is the derivative? The left hand side is dy dx, the derivative equals, and here we have on the right hand side we have to use the chain rule, right? So the derivative of the outer function is e to that same power, right? E to the power c1x, and then times the derivative of the inner function, which is c1x. Well, the derivative of c1x is just the constant, right? c1 times c1. In other words, it's c1 e to the power c1x. Now, that's the derivative. This is not quite the differential equation yet, because remember, in the differential equation, we don't have those arbitrary constants. So to obtain the differential equation that describes this family of curves, we have to get rid of this arbitrary constant. And to get rid of it, well, we have to go back to the original equation and try to solve for that constant. So let's try that on the side. So what we're going to do right now is from our original equation, I guess I'll rewrite it. Y equals e to the power c1x. So how do I solve for c1? Well, I guess if I can solve for c1x, that would be good, right? From there I could get c1. Well, here simply we can it's an exponential equation, right? We can switch to logarithmic equation, or we can apply logarithms to both sides. So either way, it would be good to know which one you think is the easiest. Let's say we apply logs to both sides. So we can choose the base. Now, which base works the best here? Well, since we have base e, let's choose that same base for logarithm. So in other words, we're going to be applying a ln to each side. So it's going to be a ln of y equals ln of e to the power c1x. And then now all that was done so that we can bring c1x and put it in the front. So we have ln of y equals c1x, ln of e. Now what is ln of e? ln of e equals 1. That's 1. So that part is gone, right? 1. That means that I am left with ln of y equals c1x, and then from here I can see that so c1 equals, if I divide both sides by x, I'll get ln of y over x. Okay, so that's what c1 equals to. And now we're going to replace c1 in our, well, yes, we have two instances of c1 in our derivative with this expression, and that's going to be the actual differential equation that describes the original equation. So let's try. dy dx equals c1, I'm replacing with ln of y x, and then that's, okay, what are my colors? E to the power, again, c1 is ln y of x, oh no, I'm sorry, over x times x. Now looks like x's are going away, right? They're gone, and what we have is ln of y over x times e to the power ln of y. Now, from the property of logarithms, we know that if e is being raised to the power ln of something, well, that basically equals to that something, right? So all that simplifies to y. Just if you need to refresh properties of logs, please do that. That's one of them. So that equals to y. Long story short, we have the following expression now. I'll continue here. It's ln of y over x times just y. Or if I combine it all together, it's going to be y ln of y over x. Okay, here's our differential equation. I'm going to write it down once again. It's a very long line, so let me rewrite like that. dy dx equals y ln of y x. Now that differential equation describes our original family of curves, right? And it's related to the slopes of the tangent lines. Now, how do we now jump and connect all that to that other family of curves, that is the orthogonal trajectories, to our family? Well, to that we have to remember once again the relationship in slopes, and that they're negative reciprocals. So if they're negative reciprocals, that means that the differential equation of the second, the orthogonal family, will be negative reciprocal of that. So I'll say, write the differential equation how do I say it, of the second and that's the orthogonal family, of the second orthogonal family. Okay, so this is how it's going to look like. It's going to look like this. dy dx equals negative reciprocal, so I have to flip this quotient and then change the sign. So since it's positive, it's going to become negative, and it's going to be x over y equals, x over y ln of y. Now, what do we do next? Well, next, as we obtain the differential equation for that second family, how do we obtain the family itself? Well, by solving that differential equation. So I'll say step 3, solve the resulting differential equation to obtain the orthogonal trajectories. Now, the way we solve it all depends on what kind of equation we have in front of us. Let's look at what we have here. So far we've learned linear equations, we learned separable equations, and we learned homogeneous equations, right? So what kind of equation is that? Well, hopefully by its form, dy dx on one side, and then the quotient on the other side, you hopefully recognize that it's a separable differential equation. So let's separate it. Let's put everything involving y on one side and everything involving x on the other side. It's just can be done by cross multiplication, right? So the left hand side will be y ln of y dy, and the right hand side is negative x. I'm keeping negative with the right hand side, dx, right? And once we separated variables, now we just simply integrate both sides, right? So we integrate both sides. Let's see, we shouldn't have any problems with the right hand side, so maybe we can like leave it alone for now. Let's integrate the left hand side, since there will be, you know, a few steps involved. So I'll do it in a different color. It's my scratch work here. So integral of y ln of y dy. So what method do we use here? Well, it looks like since we have two different types of functions combined together, integration by parts, right? That would be a good method. So let's say that u is ln of y. Remember, when we have ln involved and we're doing integration by parts, we have to let u be equal to ln of y, since we can't integrate that, right? We can find its derivative, which we'll get into in a second, but we can't find it its antiderivative. So u has to be ln of y, and that means that v prime is, well, y. Now derivative of u prime is 1 over y, right? And antiderivative of y, which is v, is going to be y squared over 2. Let's put it all together. So according to the formula, if we had u v prime, here we're going to have to put just u times just v. So u times v, I'll say y squared over 2 ln of y minus integral, and now we have to switch the order. So we had u v prime, now we're going to be using v u prime, right? So in other words, or u prime v, either way. So that's 1 over y times y squared over 2 dy. Okay, that's y squared ln of y over 2, maybe I'll write like that, minus, so what's going on here is y, and then that square will cancel. We have 1/2 that we can put in the front of the integral, and we have just y dy. Okay, y squared ln of y over 2 minus 1/2. Antiderivative for integral of y is y squared over 2 plus c. We can put the constant here. And that is y squared ln of y over 2 minus y squared over 4 plus c. Perfect. Okay, so that was the left-hand side. We said the right-hand side is a little bit easier, so we can write it down, you know, right away. So copying that equation, or results of integration. The left-hand side, y squared ln of y over 2 minus y squared over 4. Now I said c over here. If we follow our definition of orthogonal trajectories, in that definition the constants that we use within both families of curves are c1 and c2, right? So if you look back to the question, we can see how it's the arbitrary constant is c1. So technically I better use c2 over here just to be consistent with the definition. As you remember, it doesn't really matter, but you know, to make that look close to definition, I'll use c2. So plus c2, that's the left hand side, and the right hand side is integral of negative x is negative x squared over 2, and we're not going to write constant here, since, you know, we just keep that as the constant. With that said, let me go back and Actually, now erase that to over here, right? Let's just say C, right? That was the constant of the integration on the left-hand side. And that C2 is the one that will combine constants from both sides. So now let's keep it like that. Hopefully you're not confused by now with those constants. We can always rename them and relabel. But yeah, that's what it is. So we found, or we solved the differential equation, and we obtained the corresponding family of curves, right? Well, that's the solution to that differential equation. And that's the one that we call the orthogonal trajectories for our original family of curves. I'm gonna leave it like that. Remember how we can use, play with constants here. I was gonna say I'm gonna multiply everything by 4. Again, I'll have to rename C2. That's fine. No, let's do it. So I don't like how we have so many denominators here and they're constant. So let's multiply everything by 4. If I multiply everything by 4, then I'll have 2y squared ln of y minus y squared plus 4c2, so I'll have to get rid of that c2 now, equals negative 2x squared, right? If I multiply everything by 2. So at this point, guys, I'm just making my equation look, I don't know, a little bit better. But that's a good answer anyway. And I will relabel 4c2. I was trying to keep c2 for my final answer. You know what I'm gonna do? Okay, so this is C. Let's call that C1. Oh no, I can't do C1, right? C1, we had an original family of curves, so that was C1. Now here we have C. Let's call it C3. It's a little bit silly what I'm doing right now, but as you can see, I really want to have my answer with C2. So C, that's C3. And now for C3, I'm going to relabel as C2. Okay, here it is. I got what I wanted. I'm going to box that. But yes, that is the final answer. And that's the orthogonal trajectories for the original family of curves. So as we look back to the whole process and we think about it, then as we look at the corresponding differential equations, let's just say corresponding derivatives, which represent slopes of tangent lines, we'll see that they are negative reciprocals. And that was done, well, by us, we kind of forced that, but it was done here. So since they're negative reciprocals, it means that all curves in the original family are orthogonal to all curves in this family. And it would be a good exercise, additional exercise, to graph or to pick one curve from each family by substituting the constant or arbitrary constant with any number you like and graphing them. It's a little bit tricky to find, so of course we need to use some graphing tool for that. It's not in a good form, so most of the basic graphing tools online don't like this form of the equation. We're going to try that with the next example with you, but again, it's a fun exercise. If you can put, especially if you can put your families or of curves or those equations in the explicit form, then try to graph one member of each family and even like visually see if they look like they're orthogonal curves. So that's example 1, and we're going to have one more example to try.